In this video, we're going to talk about how to write equations in the form y equals ab to the x, which would be your typical exponential function. It would be an exponential function that has no transformations being done to it. So when you have a function that looks like this, we know a few things about the graph and about the actual way the function is growing or decreasing. So the a value is always going to give you your y-intercept. So that's something you'd be able to look for if you were looking at the graph or even the table of values. And if you're dealing with a word problem, then we also refer to this as our initial value. It's really like the starting point of the function. The b value tells you how the function is growing or decaying. So this is referred to as the growth or decay rate. It's sort of like the slope of a linear function. It's really what tells you how the function is going to be moving from left to right. So the b value is going to tell you a couple of things about the actual function. So when b is greater than 1, that means that we have exponential growth, or that the function is increasing from left to right. B cannot be equal to 1, that's why it's strictly greater than, because if you had that b was 1, the value would just be 1 over and over again, and that would actually turn into a linear function. If b is between 0 and 1, meaning it's smaller than 1 but bigger than 0, that's going to lead us to have something that's decaying exponentially. Again, we're avoiding it being equal to 1 for the reason I just described. It also can't be 0 because that's kind of like 1. If you keep raising 0 to a power, you're just going to still get 0. And if you had a negative b value, you would actually have alternating positive and negative values, which won't end up looking exponential at all. So that's a totally different type of function. So those are just kind of the general parameters of an exponential function in that format. So now let's look at a few examples. So these are just kind of the most basic thing I can ask you to do. This is just a description of how a function is growing or decreasing exponentially. So this first example has to do with finances, which is a very popular application. It says you deposit $500. That means that's really like our initial value for this function. So that's going to give us our a. And we are told that we're accumulating interest, meaning the amount in the account is growing at a rate of 2.5%. So when you're told that, you can make your b value by taking 1. 1 really is like that 100% of the $500 that you start with, and you're adding to it that 2.5%, but we always convert percents to decimals before we deal with them, which really means we're dividing by 100. So this is really the same as 1 plus 0.025, not to be confused with 0.25, which is 25%. So the b ends up being 1.025. So the equation that would model this growth in this account would be y equals 500 times 1.025 to the x power. So if you were to plug different values in for x, that would tell you after so many years or weeks or hours, they didn't actually tell us the time in this problem, but you could plug in any amount of that time and it would tell you how much is in the account. Okay, so let's look at an example still dealing with money. So depreciation of a car, that's another very common application. But this time, since it's depreciation, this is going to be exponential decay. So we still are given that initial value. So that $28,000 that you bought the car for is your A. And since it's depreciating or decreasing at a rate of 6.2%, very similar to how we constructed B in the last example, except now we're doing 1 minus because you're losing percent out of that 100% that you started with. So again, you would have to take your 6.2 and divide it by 100, which would be the same as moving the decimal point 2 places to the left. We're going to get another single digit percent, meaning don't use 0.62 because that's 62%, so be careful. And that gives me a b value of 0.938. So then again, I can write out my function. So then I have the 28,000 times 0.938 to the x would model the depreciation of this car, and it actually told us this time per year. So I could plug in a 5, a 10, or whatever to kind of find out how much this car would be worth in X number of years. So kind of notice some of the things that we talked about at the beginning of the video. Here my b value is greater than 1, which implied exponential growth. Here it's smaller than 1 but bigger than 0, which implies exponential decay. Okay, so now we'll look at a different context of an exponential function. So this time we're given a table of values. So the reason we know that this is exponential and not like linear or some other type of function is the way that it's actually decreasing. So in this case, you can see probably what stands out to you the most is that these functions are being cut in half over time, right? So one way you might think about it is, oh, you're being divided by 2, but when we do an exponential function, we need to make sure the b value represents what's being multiplied by over and over again. So instead of looking at this like division by 2, we look at this like multiplication by a half. Because remember, if it's decay, we want our b value to be smaller than 1, so using something like 2 wouldn't really make sense in this case. So just by noticing the pattern, we're actually given our b value. The other thing that we need is our a value, which in the word problems we looked at the initial value given, but now we're looking more from like a graphical perspective. So we're looking for when you have your y-intercept, which would be when x is 0. So in this case, our a is 100. So then that means the equation that would match this function is 100 times 1/2 or 0.5 to the x. So if you really wanted to check that, you could go put that in the y equals in your calculator and then go to the table function, and you should be seeing 0 is with 100, 1 is with 50, and so on. Okay, so that would be an example of writing an exponential function from a table. Now we're going to move on to more of a longer word problem. This strategy, by the way, would work for if you were given a graph and you knew a couple of points, really any situation where you're given enough points to really see the pattern that's happening. This strategy would work. Okay, so now we're given really a full-on word problem, so we're not told any percents here or anything like that, so we can't treat this like the first couple problems that we did. Instead, we're given really 2 snapshots in time. So we're talking about exponential growth of a population of bacteria. Again, another popular context for exponential functions. And it tells us 2 things. After 3 hours, there are 100 of them. And then after 8 hours, there are 350 of them. So clearly this is growing fairly quickly. So, with a 5-hour gap, you increase by 250 bacteria. So we really need to know specifically how that's growing. What is it multiplying by each time for that 100 and that 350 to happen when x is 3 and x is 8? So we're really going to look at this like 2 ordered pairs. So right now we know that 3 being time goes with 100 bacteria, and 8 goes with 350 bacteria. So I think the best way to look at this is actually make yourself a table, kind of like what we had in the last example. Even though you're going to have a lot of gaps, at least you can start looking at the pattern in a more visual way. So usually when I do one of these tables, I like to leave room for 0 because, as you saw, the 0 is an important value that's going to give us the y-intercept and ultimately the a. So even though I don't know it, I'm including it. I know that 3 goes with 100. I don't know 4, 5, 6, or 7. These are all blank. But then I know that 8 goes with 350. Okay, so it's kind of annoying to write that whole thing out, but again, it gives us more of a sense of how many times something was getting multiplied to get from one value to the next. Okay, so now that you have this visual, let's set up a little equation to model what's happening. So we know that when you were at 100 bacteria, you multiplied by something 5 times, 5 jumps in the table to get to where you had 350. So I can model this by writing 100 b to the 5th equals 350. If you have trouble counting in your table and you're never really sure where to start or where to end, really just think about it. What is the difference between the 2 x values that you have? So there are 5 kind of time periods of 5 hours between there, which is why we're doing b to the 5th. So now we just have to solve this. So you want to first isolate b by dividing. So now I have the b to the 5th. So I calculated this to be 3.5. You could even just keep it as 350 over 100 if you wanted to. What you never want to do here is round this number. So even if the decimals come out really ugly, like there's no pattern, just keep it as exact as you can, and you can really just store your answer in your calculator, which we talked about in class. So now, to get rid of the 5th power, we actually want a 5th root. So I'm going to take the 5th root on both sides of this function. If you're not remembering how to do this in your calculator, if you're using a regular TI-83 or 4, you're going to have to type the index of your radical first. So you'd actually have to type a 5, then go to your math menu and choose choice 5, and then type in your 3.5. If you're putting a fraction into something like this, so let's say you kept the 350 over 100, you're going to have to put that fraction in parentheses, so just keep that in mind. It did tell us in the problem that we could round to the 100th for b, so I'm going to go ahead and do that. And in my calculator, that would be 1.28. Awesome. So I've got my growth factor. That means if you multiplied 100 times 1.28 roughly 5 times, you should get to about 350. Now again, if you go back and check, it might not come out perfect, but you have to remember that we did round, so that's why we're going to be a little off. Okay, so the only problem here is we still don't know A. So I'm going to have to now think about going backwards. So I know the growth factor now. So if I can divide by that number, it would take me 3 times of going backwards to get to my y-intercept. So I'm going to take the highest value I have in my table, and I'm going to divide by the b however many times I would have to go backwards, which in this case is 3. So the shortcut here, instead of dividing 3 times, is I can do divided by 1.28 cubed. So again, if you're not comfortable with doing that on your own, you can simply do 100 divided by 1.28 3 times until you get to your answer. So if I put this in my calculator, and I'm noticing that it did tell me to round to the nearest integer, which is like the nearest whole number, I get about 48. So this comes out to approximately 48 bacteria. Makes sense that we're doing a whole number because a bacteria is technically a living thing, which is why we're not rounding it. Okay, so then we have everything that we need. So the equation to model this bacteria growth would be y equals 48, that's what we just found for A, times 1.28 to the x power. Make sure you put that x on there, because if you don't, then you've really just written me 48 times 1.28, and that's not going to model this growth over time. Okay, so we've written the equation. There is a follow-up question. It wants to know how many bacteria do you expect there to be after half of a day. I know I wrote over this a little bit, but hopefully you can still read it. So this is where I would just say go back and check if you don't remember what the original function was talking about. It's measuring in hours. So each of the pieces of information that was given was in hours. So that means you have to be plugging in hours for x. Well, I think you guys all know that a full day is 24 hours, thus a half day is 12 hours. So I'm going to write out the function I just came up with in part A and plug in a 12 for x. Okay, and again, even though it doesn't say it, this is a living creature, so I am going to be rounding to the nearest whole number just because that makes the most sense. So sometimes it's not specified just because you're supposed to use common sense when you think about the context of the problem. So this comes out to, for me, to about 928 bacteria. If you're following along and really want to be practicing, I recommend just pausing the video in between before you hear me say the answer. I know it's a little late to tell you that, but hopefully you're trying it out and you're getting the same answer as me. So that was a little overview of how you can write the equation of an exponential function given a variety of different ways that the problem is presented to you.